So today we are discussing complex numbers. Now, another name for complex numbers, and another way that we talk about these, is imaginary, which doesn't really mean like imagination. It's just saying this doesn't work out in our physical realm that we do mathematics in. Now, that doesn't mean we can't do the mathematics. It just means it doesn't work out to real values that make sense with how we understand mathematics. So when we talk about imaginary numbers, they're numbers that we can deal with, but they are non-real numbers. So that's why we call them imaginary. So if you want another synonym here, you can say imaginary just means non-real. So it's not actually imaginary, it's just they're not real physical numbers that can be used.
Because they can't exist.
In the realm in which we're doing our mathematics.
In another universe, they probably exist.
They could, yes.
I feel like you usually have an answer for these questions, but I feel like this is the only one you're not. Maybe what I'd actually use is in a setting outside of math.
Yeah, your argument with any answer that I make is going to be that's like, it's all going to relate back to its math.
Well, I mean, but like, probably for Pythagoras, you could really landscaping, which is.
But it all relates back to math.
But like, those are you can pull skills from that using other things besides math.
So let's look at some of the actual understanding it before we talk too deep about it.
Okay, but when is your job? If you're not a math teacher or a mathematician, when is your job to be like, okay, use imaginary numbers?
So part of math and a lot of math.
Trust me, if I lecture someone on imaginary numbers, I'm trying to get this. That's what you should. If you lecture someone on numbers, you're pretentious.
We just bought another set. I'm not getting his rainbow. We have one Tupperware coming up.
Push that up, baby.
Guys, he's waiting.
Sorry.
I have a lot of patience. It's okay. So let's look at some of the understanding of what we're doing before we talk too deep about the application. Because really what we're saying is in a lot of these situations, we will end up with one real solution and one non-real, letting us ignore the non-real and look at the real. So one application is for identifying what solutions work, as opposed to what solution does not work, and then throw that one away. So, when we talk about imaginary numbers just from the base, this is how we can express the radical of a negative number. So before we told you that we can't, well, we lied to you. We really can take the square root of a negative number, but the result is not a real number. So the result then, we break up the square root of negative 5 to say we're really doing the square root of, and this right here in the middle, I wish that they had, maybe they do. Yeah, so they break it up to the fact that instead of thinking about negative a, think about negative 1 times a. You're going to break up your value into its products, the factors that make that value. Then, when we look at square roots, we can separate them out and say the square root of negative 1 and the square root of a. Because now square root of a is going to be a rational or a value that we can look at. It's a real number. But the square root of negative 1 is not, so we just turn that into I, or the imaginary number that represents radical negative 1. So if you are not comfortable with this yet, I is just a placeholder for radical negative 1. That is the value of I, but because it's imaginary, that's why I put value in quotations. Yeah.
Okay, I have an unrelated question, but I won't be able to focus until I get it out.
Okay.
Is M term next month?
No, May, not May.
Dang it!
After testing.
I was just thinking about it, I was like, next month starts with an M.
No, and really when I talk about it, I talk about May term. So we can define operations on the set of complex numbers so that when we restrict the operations to the subset of real numbers, you get familiar operations on the real numbers. So that's essentially what I was saying with the application of when do we use this. Sometimes we use it so when we look at our list numbers. Some of them are complex non-reals that then limit my solutions to the real values. And every quadratic equation has complex number solutions that are sometimes real numbers and sometimes are not real numbers. So when we talk about a complex number is really like an expression. It involves a value and then an imaginary value. So my complex number has a real part and an imaginary part. So now when we talk about our coefficients or our values a and b, we can talk about a real part a and then some coefficient on my I if I were to need that. Any questions on the fact that a complex number is really talking about like an expression where we have a real part and an imaginary part? That's what makes it complex. Like complex figures, you might have a prism with a pyramid on top. So imagine that prism as the real part and the pyramid as the imaginary part, or however you want to think about that. Okay, that annoys me, that I can't take a screenshot if there's no ink on the screen. So, just to start with the core basics. If we look at radical negative 18, the first thing we do is split it to its negative and then the real value itself. So we split it to negative 1 and 18. We then can turn the negative, or the square root of negative 1 into I, but then when we go to evaluate square root of 18, we can't evaluate that and simplify it. So if you want to write the extra step right here, we look at this as radical 9 times 2, breaking that up again, and then radical 9 gives me 3, and radical 2 stays as radical 2. So now that 3 value, since this is a string of multiplication, if it helps you, this is really I times 3 times radical 2. Sorry, 2. We can rearrange and we put my 3 in front of my I. So now I see I have 3I radical 2. That number involving the imaginary number makes the whole number itself imaginary. So that value of 3I radical 2 is not a real number that we can use, but it is a value that we got. It's an answer. Caleb?
Would it be possible to get an imaginary value without a radical?
The only way that we end up on the imaginary number is by taking the square root of a negative.
Which confuses me. No, I say when I say without a radical, I mean like we had like the radical 2.
Yeah, so imagine if this was radical negative 9.
Okay.
Then we would just get 3I
3i.
without the radical 2.
So then like in terms of like adding imaginary numbers, how would that work?
So I is not a variable.
Okay.
I is a value.
Is a value just substituted?
Yeah, so hang on to this. Again, we're at the very beginning of the lesson. You're asking questions like further down the pathway. You're running ahead of us, Caleb. Wait for the group!
I'm asking the things that were on the test. That didn't make any sense.
Not on the quiz. There should not have been any.
I think you need math testing.
Oh, yeah, but that's on purpose. That it pushes you all the way to, hey, you don't understand this yet. So try this on your own. Break this up into what we can evaluate from the square roots. First thing we do is break it into 1, and I would start again just so you can work left to right. So I would start with negative 12. Sorry about my one radical. There's a section of the board there that does not like me apparently. So the first thing I want to do here, Michelle? So the first thing we actually do is negative 1 and 12. But then down the road, we can break that 12 into 3 and 4 if you want. So I can go ahead and do that there if you want, I guess. So we still have the radical of negative 1 and the radical of 12, which we can break into 3 and 4 if we want. Now we know that radical of negative 1 is actually my value I, but when you look at evaluating the 4 and the 3, what of those can pull out? So this becomes 2I radical 3.
How did you get it up?
Because radical 4.
Yeah, I get it now.
The radical of the 4 became our 2. Yeah, so I tried to hit the other one, but apparently it didn't like me.
I was like pink.
No.
I'm like colorblind.
So, this is when it gets really weird. So just give me your eyeballs for a second. Or look at your notes. But we can graph this solution, even though it's imaginary. We use it by graphing on the complex number plane. Our complex number plane is going to have an axis that is our real values and an axis that is our our imaginary values. So our real values we use on our x-axis. Our imaginary values we use on our y-axis. So my solution, if it's -5 plus 3i, that is going to go to -5 on the real axis, and then 3i on the imaginary axis. Notice that my imaginary axis is labeled by i's. You cannot say this is the I-axis and just have like 1, 2, 3. Does not work like that. I is not a variable. I is a value. So we have to label that's 1i, 2i, 3i, 4i. We got to use that as part of our values. Any questions?
If we typed in radical negative, what is the calculator? Would it come out as that?
It'll probably give you an error depending on how smart the calculator is.
What if it's a graphing calculator?
So your graphing calculator, don't quote me on this because I'm not certain that it can't, but it is not going to think like this. It is not going to change its graph into a graph that can graph imaginary numbers. Its graph is x, y coordinate plane, period, done. Because remember, it's a dumb computer. It can only do what you tell it to do. It can't really think through imaginary numbers.
It just says non-real.
That's like telling a computer, hey, you can't do this because it breaks the parameters of mathematics. Now try it. Like, it just doesn't work.
Yeah, Caitlin.
So only humans can do this?
Only we can understand it. We can use computers to help us, but the computer is immediately going to think, you've broken a mathematical rule, you can't do that.
Can you program the computer to understand it?
So that's why, actually, that's a really good question. That's why we start with the split. That right there is why the first thing we do is take out the part that the computer can't think about, and then it could do everything else, but we have to take out the imaginary part first.
See, my theory is that the computers actually do understand it, they're just not saying anything so that you think they're dumb, and then when they take over as our overlords, they're coming after you first because you keep calling them dumb.
So, now, wait, hold on. The absolute value of that number. Do we see what this is actually doing here? So it takes the absolute value of -5 plus 3i.
When there's regular.
Can you only graph one? That would be without the imaginariness.
So the absolute value is talking about what?
The positive.
Mm,
Well, I mean 0.
Distance from the origin, right? Which normally we're talking about is 0. So here, still 0 reals and 0 imaginaries. That's our origin. So when we talk about its absolute value, we're talking about how far away from the origin is it. So we're essentially doing our distance formula, or Pythagorean theorem. So we take the square root of our real value, our real value squared, our imaginary value squared. Because think about it. If I have 3i squared, and you want to probably jot a couple notes right here, because otherwise you'll be real confused on your homework. This comes out of taking 3i and squaring it. But what that actually does is it says, okay, do 3 squared and I squared.
Wouldn't I squared be 1? -1 times -1 would be 1. It's the square root of -1. Oh yeah, I forgot the square
So
root.
if I is radical -1, then that squared, we're saying, is -1.
Yes.
That yes had a dot 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 on it.
Take the square of a square root, it just undoes both of them. really tough.
What
Would it just go negative 9?
So when we're looking for the absolute value, it then makes it positive, and we really can just say it gets rid of it. So when we look for the absolute value and we set up the absolute value here, which turns into our manipulation of the distance formula or the Pythagorean, essentially your I just disappears. Because we're squaring it, which turns into a negative 1, but we're only looking at the positive, or the distance. The absolute value makes everything positive, so essentially our I just disappears. So really, square your value, square your coefficient, add them together, take the square root.
Why does it disappear?
Let me see how far we get today, and let me see if we can break one of those down a bit further. Give me a minute to show you a couple more of these and see if this makes sense. So, we can use this same graph. So we're going to use the same graph above. The graph of 6i. What is its real value?
Wouldn't it be 36?
Hold on. So if I look at 6i as a complex number, because it's got an imaginary part, does it have a real part? No, because this 6 is part of the imaginary part. So if I'm going to graph this on my graph, this 6i, it's just right here, it has no real part.
Wait, are you referring to the absolute?
Yeah.
Wait,
But first, we put the point on the graph. Just like we had first put negative 5, 3i on the graph. So now what we're asking is what is this distance? Right? What is that absolute value?
36.
So if I set this up, this becomes square root of 0 squared because there's no real value. And this is 6i squared.
Why are you adding in the 0 if it doesn't do anything?
Because it was here, so I didn't want you to get confused why they have it, because that's our real part and this is our imaginary part. Because if we look back at what makes a complex number, even if it doesn't show up, a complex number is technically a part that's real and a part that's imaginary. So here, we just don't have a part that's real. So that's 0.
Did you draw that circle?
Yeah, this.
That's a really good circle. That is.
Thanks, I've been having trouble with circles
Did you
lately.
practice?
So, so we only care about the positive or the value that we can get out of this based on absolute value. So this all becomes, again, the I essentially gets rid of itself because when you square it, and then again take the square root, and only care about positive values. So 6 squared is 36,
Oh, so just be.
and we get radical 36.
Wait,
Where does the I go?
The I is imaginary, so it doesn't matter.
Wouldn't the 6
I'm just
and
going
then
by
the radical?
Yeah, where did the I? What?
Wait, no, I have an
Go
idea.
where?
Continue on.
I think the.
How?
So, if the distance is 6, wouldn't that mean that I is 1?
In this graph, sure, because we've made that, bless you, our units, like 1i, 2i, 3i, that's our units.
No, but if that distance is 6, and the point is at 6i,
Because we are making a real representation of imaginary values. Yes.
but I doesn't equal 1. It's the square root of negative 1.
I know, I agree. Hang on. This stuff is really weird. So, try another one with real and imaginary. So, you can do it on the same plane if you want. What we had used green. Hey guys, talking to each other about things that aren't math are especially not going to help you. So I go to 5 and then negative I right here.
If it's negative I, then never mind.
really 5 minus I.
But that
Because
doesn't.
I is a value, isn't it?
How can you
Could it
minus?
So the problem is I'm trying to figure out how to explain this in a way that makes sense. You're getting stuck on the thing that everybody gets stuck on, which is it's fine. Don't feel like you're having issues you shouldn't be having. You're having the right issues right now. You're trying to think about this using the knowledge base that we've taught you through all of mathematics. And you can't. Because we are breaking mathematical rules right now by saying that imaginary numbers can be plotted and that imaginary numbers can be worked with. So we are now kind of like, we stepped into this special realm where we let certain things happen that can't really actually happen because they're imaginary. Caleb, I think you
So
had it
wait,
up first.
we just like I mean in this case, like with this like 5 minus I, instead of treating I like a variable, could we treat it like an actual value?
It's not a variable.
Yes, that's what I'm saying. Will we treat it like an actual value, not just some thing?
Yeah, so like our y-axis is in the scale of 1i. So every block or box is a distance of I. But the problem is the distance of I is not a distance we can actually talk about.
So instead of like a variable, which is like 5 minus a, you couldn't finish that. That's just done. With like 5 minus I, you could per se like finish it.
Because like 5 minus a is going to be determined by what is a.
But I is a
We
set value.
know I. Yeah.
Alright.
So we're not trying to graph like a line or a function or anything like that. We're trying to figure out where does this number exist, although it doesn't. So this whole graph is an imaginary graph.
That's like theoretical mathematics.
Yeah, exactly. We're doing all this in theory. We can't physically actually do this, but we can make a model to do it. Lynn.
So couldn't you just like use algebra and find I?
No, because I is not a variable.
But
So that you're still treating it like,
Well, then what are you supposed to do with this?
okay, right now, all you're supposed to do really is try to absorb and understand the math. Don't understand the theory behind it, because we're going to go deeper into that once you get some like understanding of how we do the math down. Don't try to understand the theory yet. Just try to understand the math.
I'm
Do
trying to
you-
understand the math, but I just don't know what to like. I'm given 5 minus I. What am I supposed to do with it?
So we went 5 distance real on our real axis. So we really could walk 5 down that axis. Now the imaginary axis, the thing that breaks the math rules, we go down 1. So we went down 1. Now we're saying comparative to the origin, if I went from here to here, what is that? That's our absolute value of 5 minus I. Because absolute value is actually distance from 0 or distance from the origin. Yeah.
So if you're like solving it, would you do like square root of 5 squared plus 1 squared, or would you do plus 1x squared, or would you do like square root of 5 squared? But I just have to. It's like in the past one you use a 6, and you do like 0 squared plus 6 squared. So would you do like 5 squared plus 1 squared, or would you just like not have that since the I disappears?
So this has a coefficient, right? So that's what we have to look at. So your question was phrased exactly how we want to be thinking. So Michelle said, what do I really look at here since this had a 0 for the real value, and now we have a 5 for the real value minus 1i, or negative with a negative 1i, if you want to say it like that. So we could rewrite this as 5 plus negative 1i. Yeah?
Since we're doing absolute value, do we really have to care that it's a minus instead of a plus?
I mean, eventually that won't matter.
Yeah, that's the thing.
But yeah, we kind of, because that'll be the same distance as if the point was here.
Alright, yeah, because that was
If my
just
smart
like,
board
does
worked
it really matter that it's a plus or minus?
No. But I mean, we want to know that our point is here as opposed to
Not instead of-
there.
okay.
But distance wise, it won't matter.
Alright.
Yeah, Brian?
Why would you want to plot it? Like, that just seems like more work that doesn't get you anywhere.
Again, you're going
It's a
too deep.
visual
You
representation.
just start to understand what we're doing, then we'll get to the why. This is still in the whole, like, I might think back on this lesson and be like, man, that sucked. I totally need to teach this differently next year. Complex numbers are weird. I'm still working towards being able to teach them effectively. So I wanted to get a gauge on us today. This is obviously, we have a lot of gaps or whatever we want to say. So I'm going to pull materials and find resources and design more lessons to follow this to fill in those gaps. But all we're trying to do right now is understand the math that we're following through.
Okay, so would the absolute value just be 5 plus I?
No. So you're thinking of absolute value like we do with regular numbers, like rational values that we have. We here are talking about absolute value as distance, because absolute value really is always talking about distance. But when we talk about distance in the real mathematics side of like just values plotting on the real plane, that's easy to think about. Here we're talking about distance on an imaginary plane, dealing with imaginary units. So what we would do, just like we did up there, is set up the square root of, well, my x distance was 5.
Why are we square rooting it?
Because we're doing distance. So our distance formula is radical the x distance squared plus the y distance squared. Because it's your horizontal and your vertical. So then my y distance squared, whether it was negative 1i or positive 1i, doesn't matter. The distance it went was a distance of I. So it's really negative, but that doesn't really matter, as Caleb already pointed it out.
I like it.
How do you like this? No.
This becomes square root of 25 plus 1. So we get radical 26. But here's the big but right there. That radical 26 only works when we're talking about this plane, the imaginary plane. So this distance right here, what we found out, is radical 26 in that plane.
Why do we put a 1 in front of the I? Like, if it's imaginary, couldn't it be like anything?
It's not, so I has its value. It is radical negative 1. So this is saying minus a radical negative 1. So go this far real and then go down a unit of radical negative 1, which there is no real thing as a unit of radical negative 1. So we made it up.
But isn't I just radical negative anything?
No.
No.
I is always radical negative 1. That's what it represents. That was one of the first things we wrote down.
Only radical negative 1 is imaginary, but radical negative 8 wouldn't be imaginary?
Any square root of a negative involves an imaginary, because you cannot. So you can't square root negative numbers, right? We can't, quote unquote. You've always been told you can't. It doesn't work. So now we've stepped into this realm where, okay, we can't do it, but if we made it work, how do we make it work? So I'm going to say for the next few minutes, no questions. It's chill. I will take as many questions as we have, but not right now. We're going too far away from where we're trying to go.
You know what? This one's about the problem, though.
Okay, what about this problem, though?
So, like, what you said, it was the square root of 5 squared plus, in parentheses, negative 1i, comma, squared with the still the square root over it. So the square root and then the squared would get rid of each other. I get that. But then obviously you have negative 1 times I, which would just turn it essentially into the square root of 1, right? Which is why it's 25 plus 1. I think that's what I'm getting at. So
I think, if I followed you correctly, I think.
Alright, so then had that value been 1, would this have been like a solvable? Then
So negative 1 squared and 1 squared both give you the same thing.
Oh yeah. Wait.
Negative 1 squared, like
Oh,
negative
squared.
1 squared is 1.
1.
1 squared is 1.
Oh, okay. So you. Oh yeah. So you do the square for. Okay. I thought it was different, but okay.
So, because this part's not that bad. So, hang on to your horses. We'll just understand a bit of the math. Then we'll go deeper into it tomorrow. We'll take a lot of questions. When we talk about summing our complex values, we treat this just like we would our old school binomials. So we want to use commutative and associative properties here to regroup, put reals with reals, imaginaries with imaginaries. So this is going to become what? After we move everything around, well, so we get 4 minus 4, or 4 plus a negative 4, and a negative 3i, and a positive 3i.
Big O.
So do B, and then do the got it.
Wait. Okay, this isn't necessarily. This just about like order of operations, because I'm not very good at those. Can I just do the negative times the values? Like, can I just do negative times negative?
Talking about
2?
for subtraction.
Yeah.
Yeah, so you can
Minus.
distribute your subtraction first, is what
Alright.
you're saying.
Proceed. Okay.
And this really becomes this. You saying do that?
Yeah.
Yeah, you
Alright,
can do
cool.
that.
I'm allowed to do that? Alright.
Yeah.
So I get screwed up sometimes.
So although we have stepped into that realm of doing math that we can't do, this all works following the same algebraic rules that we've had. So even though we're in this like special little space where we're doing math that can't be done, we still follow those algebraic rules where we're grouping like terms, real values with real values, imaginary values with imaginary
So
values.
like basic math principles still apply
Even though we've broken one, yeah.
So
One of the biggest math rules we've broken, but we still follow our
in
math
this
rules.
realm, a lot of your math tool rules.
Yeah, like your properties.
Plus some extras.
Yeah, and not like the extras only come from what we have to create to make this work.
I like it.
I feel like we're in a comic book.
I
know
feel
what?
like
It
the
feels
science
like
comic books.
surreal. Like
It is. It's quite awkward. So moving through, same thing works.
Like the have you ever seen
So here's where this gets nice. When we start composing functions, and guys, here's really why we're doing this. When we start composing functions, let's say we had a function of another function. That would then set up a situation like this, where we have a distributive property. So if we had 3i times negative 5 plus 2i, then when I distribute that out, and I end up with an I squared, that I squared is actually negative 1. So another rule that you might want to write down off to the side here to remind yourself is that I squared is negative 1. Since I is radical negative 1, then of course when we square it, it just takes off the square root. We're not going back to that graph right now, because this is where the confusion comes from. The algebraic rules that apply are different than when we try to put it in some geometric. We try to do it graphically. Megan?
Couldn't I squared be like -2?
No, because I has its value to start. This is the value of I.
But
I's
isn't
not a variable.
The square root of like any negative number.
That's not I. It is an imaginary number. I is not an imaginary number. I is the value square root negative 1. But any square rooted negative number is a imaginary number. Not that it is I. It is an imaginary number. I is what we use so that we can say, okay, this is really square root of negative 1, or we could replace that with I, times square root whatever your number was. So we use I to break up an imaginary number into two pieces. Real piece, imaginary piece. So I is the base imaginary number that is in every imaginary number that we can pull out of it. It's like a common factor. So I is the common factor to all imaginary numbers and can be factored out
So it's like the
of
one,
any imaginary
the
numbers.
one is whole number.
Yeah, it is the unit
Alright.
of the imaginary numbers spectrum, or whatever you want to say. So, we're out of time, but I want you to play with some of the algebra here. We will go way deeper into this tomorrow and take lots of questions.
Brian, have you ever seen those like what do they call it? Have you ever seen that like
This is the one thing that I wish I didn't have to teach. Because it's just really complicated to understand. But once we get past that whole, like, this doesn't make sense, because it doesn't. But once, well, you use like really weird science. You guys have your stuff separate from your body.
Oh, they were like, use the revolution of the moon.
Yeah. These all relate to our quadratics, where one result is imaginary and one result is actual.
Alright.
Mr. Hudson,
What?
I thought you
Oh,
were
yeah.